start. I'm sure we'll have more people going to join maybe in a few minutes. So yeah, so introduce Zach Olkin. He is currently a fourth year PhD student from Amber's lab by Professor Aaron Ames at Caltech. And I think Zach will talk quite a bit about his this control guided RL work for some of the robotics problem. I think it's going to be another very nice seminar, exploring the intersection, combination of, model-based and RL approach. So it will be, very beneficial for some, work we are exploring here at the lab. And with that, I think, yeah, Zach, please take it away and thanks for giving us this seminar online.
Great. Thanks for the introduction and thanks for the invitation to present. I really appreciate it. And I just mentioned this, but I actually did my undergrad at Georgia Tech and, I really liked it there.
Oh,
So I'm very
really?
happy to be presenting. Yeah.
Which group who you work with?
I worked a little bit with Aaron Young on prosthetics and then with Aaron Rodgers in the aerospace department on drones when I was there.
Oh, okay, okay,
Yeah,
cool. You are Georgia GT alumni.
yeah. Yeah.
Good. That's great to hear.
All right. Can everyone see my screen?
Yeah.
Okay, perfect. I'll just jump right into it then. Actually, one second. There we go. So I'm going to be talking about control guided RL for humanoid locomotion. And I think this term control guided RL is perhaps a little nebulous. It's definitely something we've been throwing around a lot in the lab. And exactly what it means is potentially still up for debate. But how I view this is that we're taking control theoretic concepts, whether this is like trajectory optimization or control the Lyapunov functions or something like this, and we're embedding this into the reinforcement learning to get either improved, performance or efficiency or something like this. And my main focus here is going to be on doing it for humanoid locomotion. So we're going to see a lot of walking and running. Um, Before we jump into that, I was just going to give a little bit of background on some of the stuff I did before I started doing the control guided RL. And that is, I started off my PhD doing MPC research and like MPC for hybrid systems. And so this video here shows this was some of my earlier experimental work doing quadrupedal like stepping stones. Which stones it stepped on were not um, they were not chosen ahead of time. So the algorithm chose that in real time. And then I did full order dynamics MPC. And that's like kind of what this here is showing is what the MPC solve look like. And then we can like deploy that onto hardware. And this worked, okay, it worked fine. But it's 2026. Maybe I don't have to be justifying why we're doing RL. But I think it's just always good to be thinking about these things. And in this project, I saw a lot of issues I had could be solved by RL, which is one of the reasons why I switched over to it. And so that's things like here, the compute requirements to do full order dynamic MPC are it's a lot, right? It's hard to run that on board. It's hard to run it fast enough. This is a hybrid system. And so dealing with contacts is very difficult, right? Classically, if you model the hybrid system, you end up with a graph structure and you get in like mixed integer kind of programs and things like this. And it can be really nasty to solve, especially in real time. And then there's the whole representation of your environment when you want to do something perceptive. And in this project here that you're seeing on the screen, I didn't actually do anything perceptive, but I knew that was going to be hard going to model based, doing this through model based. So I think RL really solves a lot of these things, or at least makes them easier. And so things like the hybrid nature, when you roll out your system in the training loop, it implicitly deals with all the contacts. You don't have to pre-specify this. You don't have an explicit hybrid model. And so I think this project really kind of drove home to me why I like doing RL and why I kind of moved in that direction. So humanoids, though, have come a long way because we're going to talk mostly about humanoids, right? And these are just some like screenshots from some YouTube videos, right? The bottom two are from Unitree's like spring festival, I think it was, and they had robots, right, doing flips, synchronized dance routines, kung fu, right, you name it. And the top right is the Boston Dynamics and REI, collaboration on their new electric atlas, right? And so we're seeing humanoids now do things that I think even like 5 years ago, or even less than that, perhaps people would have been very surprised to see, and would have been shocking. And I feel like I see these videos now every day, right, of robots doing all these very dynamic and very cool maneuvers. And so this really begs the question of what do we like? What do we still need to do, especially when we're considering dynamic humanoid motions? Like, where do we go from here? So I have a few research questions that I'm kind of interested in tackling. Um, and I'll talk about these questions kind of throughout the presentation. So for dynamic humanoid motions, how can we achieve the best performance and how can we minimize our tuning effort? Best performance, there's maybe a few metrics you could look at here. This is maybe like reference tracking or velocity tracking or like efficiency or endurance or something. Can we achieve any theoretical grounding for any of our work, right? I think RL involves, I would say, like a lot of heuristics and just kind of made up terms. And so can we ground any of this in theory? And can that help maybe guide some of our decisions? And then do we need human data? So I think human data is a pretty hot topic right now. I would argue that a lot of what took us from RL like working and working fine to working very well and giving us the dynamic motions you saw in the last slide was the human data and being able to track this. And just there's such good like dynamic prior effectively in the human data that it's just shown to be a very invaluable tool in RL. And so I think a lot of common methods right now will track human data references. And then this last bullet point is how can we reach autonomous dynamic humanoid locomotion in real environments? So a lot of the ones that track human data tend to just replay single trajectories. And there's work investigating, how can they generate new trajectories online, some work with like diffusion policies and things like this. But I'm very interested in how can we apply this in like a real autonomy stack. So we'll try to touch on all of these points as we go through this talk. So before we jump into the meat of the projects, I just wanted to give a little background on control-Lyapunov functions, or CLFs is how they're abbreviated, just to make sure everyone's on the same page. So with a control-Lyapunov function is like a classic tool in nonlinear control theory for generating stabilizing controllers or certifiably stable controllers of nonlinear systems. So we consider a nonlinear system of the form x dot equals f of x plus g of x u. And then we get ourselves a Lyapunov function. So Lyapunov functions are positive, definite, continuous, and they, in our case, we're always going to be looking at quadratic Lyapunov functions. So this v of x equals x transpose px is kind of what we're going to be considering. And this looks like this bowl, here in this graphic. And then the idea will be you can get Lyapunov stability, right? If you're constantly moving down your bowl, and you can prove that you arrive at the origin. Then what makes it a control Lyapunov function is this condition here, which is saying that there exists an input u such that v dot, which is what the term on the left is less than or equal to negative lambda v for some positive lambda. Right. So this is giving us our condition that says there exists an input such that we can like traverse down this bowl and then eventually arrive at the origin. And as a quick side note, this P here, we generally get through solving the continuous time or discrete time algebraic Riccati equation. And we'll come back to this maybe a little bit later, but this quadratic Lyapunov function is actually a real valid Lyapunov function for the unitary G1 humanoid that I work on. So this is like this is a real Lyapunov function, but you could potentially shape it differently if you wanted to. So then let me touch a little bit on trajectory optimization too, because this will come up throughout the talk as well. There's so many methods for trajectory optimization, right? I mean, DDP, MPPI, ILQR, direct multiple shooting, collocation, I mean, you name it, right? You can kind of keep going on and on. I wanted to deal with a trajectory optimization routine that could deal with unstable systems. So this is like a humanoid, right? That's going to fall over. Um, State constraints. And I think the state constraints are kind of critical, and I'll come back to this in a future bit. But this allows us to enforce things like periodicity and generate libraries of references. We wanted to be able to deal with high dimensionality, and we needed to be able to deal with the fact that this is, in fact, a hybrid system underlying all of the dynamics. So I ended up going with a direct multiple shooting approach. So just as a side note, for implementation, we used Casati for our autodiff, we used IPOpt for our solver, and we used Pinocchio for the rigid body dynamics. So maybe for those, if someone's not familiar with direct multiple shooting, this graphic on the right like roughly explains it, and explains it also in the context of a hybrid system. So what we see here is that when we have a hybrid system, we have multiple dynamics domains. In the case on the left, it's the flight domain, where we can see that the ground reaction force F is equal to 0. And then on the right, we have the single support, where the ground reaction force is, say, in some cone. So these are different dynamics. And classically, if you model your hybrid system explicitly, you end up with like a graph-based structure, right? Where you have all your different domains, and then you have edges that bring you from one domain to another, and maps that really map you between these edges, right? And these are like impact. If you optimize over the graph-based structure, you would like generally end up with a mixed integer program. And mixed integer program is pretty nasty to solve and not really something we wanted to deal with. And especially given that we're looking in the context right now of humanoid locomotion, the ordering of the sequences is generally like known ahead of time. So in the case of running, we have flight phase into single support, back into flight. You know, this is a periodic orbit in the state space. So what we end up doing is we fix our hybrid domains, the ordering of them. So that way we have flight goes into single support in this example. But what we can do is we can keep our times in each domain as decision variables. So this delta t flight and delta t single support at the bottom are decision variables. And then the time for each node of the multiple shooting is just an even division of those. So then that's what these lines here at the bottom represent. I don't know if you guys see my mouse. I'm not sure that gets through. But the lines at the bottom here are the multiple shooting nodes being integrated, right, for some small dt. And then the dashed blue lines are effectively the constraints. It's saying that these should match when you're converged, right? When you're feasible, the end of the original node, the end of the previous node should match my initial condition at the current node. And then we have to deal with the hybrid nature. So we have this delta impact map, and that's the map that brings us from one domain to another domain. So it's like when we impact the ground, what happens to the dynamics? So we can formulate our multiple shooting problem just like this, and we can use full order dynamics on the G1. So it's a very large system. It's a very large optimization problem. This only takes minutes to seconds to solve. It depends on what your warm start is and what exact problem you're solving. So maybe I'll talk about this a bit later when we're looking at specific problems. But my point is, it doesn't take that long to solve. And this makes it very easy for us to iterate on what we're working on. You can put in hard state constraints, which, like I alluded to earlier, is very important, I think, for what we're doing. And this allows us to generate libraries of motions. So throughout this talk, I'm going to be generating like libraries of walking and running gaits. And so it's pretty easy to do with this like direct multiple shooting approach with hard constraints. And then we only optimize a single stride. So for the G1, this is maybe anywhere from 0.3 to 0.4 seconds. I'm not even optimizing, say, left leg and then right leg. I just optimize left leg. And that's because when we're thinking about steady state periodic orbits, you can just reflect the stride from one leg to the other through like a reflection map, and you get the other stride. And then so this allows us to really get away with the full order dynamics. Because I think if you're going to do really long horizon, like optimization with this kind of setup, I think you're going to struggle to converge. So this keeps everything like pretty tractable. So now we're going to jump into my first work, which is CLF-RL. This was a REL from recently. So you can find the paper if you're curious. It's got 3 core components. It has the CLF reward, where first we take a reference, and I'll talk more about what the reference is, but we have some kind of motion reference. This goes into a control Lyapunov function, And then this control Lyapunov function just shapes the reward. It's really just like a reward shaping method. This goes into the reinforcement learning training, where we train in Isaac Lab with domain randomization and all of that. And then we zero shot deploy to hardware. And when we deploy to hardware, there's no CLFs at the end of the day. It's just a policy. And the reference motion isn't even in the observation, which makes it really easy to deploy and really, really lightweight. So I'm going to start by showing you a video of what this looks like when it's actually walking and functional, and then we'll go more into detail about the specific method. So this is us walking it around outside. We walked it on a path that goes about a quarter mile, roughly, pretty consistently. This is out in real world environments, right? So you can see it stepping on, concrete and all of that. In this particular case, it is being driven by a joystick. So I'm actually driving this thing backwards and behind the person with the camera. So you'll have to excuse my poor driving sometimes. But this thing can turn, it can walk, it can go slowly, it can go faster. There's definitely ways that I've thought about improving this and making it look nicer. And some of these things I've done and some of these things I still have to do, but this was what we had. This was about last July or maybe last August, sometime in that frame. And I'll just let this play out here and kind of show you it walking. It walks at max speed here is 0.75 meters per second. I've since increased it on the hardware and gone up to 1. I think I could go faster than 1 meter per second. And the one key here is that at this point, there is no human data. The reference generation we're talking about is all optimization and model based. So maybe it doesn't look the cleanest, although I think it's actually, I think it's pretty clean, but since there's no human data here, it doesn't look exactly like a human. It can take things like ramps and whatnot too. Okay, so let's maybe jump into the framework a little bit more. So this is effectively what we're doing. We have a reference generator, our CLF-based reward. We train an asymmetric actor critic with PPO, and we train this in Isaac Lab. So if we jump into the reference generator, in this work, we actually looked at 2 different reference generation types. So one of them is the hybrid linear inverted pendulum, which is HLIP, right? So it's the classic linear inverted pendulum, but then there's it just accounts for effectively the switching of the legs. So you can do, nice steady state motions. So this is nice because you get a linear map, and this allows us to generate the reference, I'll say online, but really it's during training is what it allows us to do. So in no situation do we have the reference actually in deployment on the hardware. It's only during training. But this means that when the robot receives a command in training, we generate a steady state walking gait with the HLIP, and then we track the reference states with the CLF reward. And I'll show you the video of this one later, but it looks kind of like you might expect a linear inverted pendulum walking robot to look like. If you've seen a lip controller before, it kind of looks like that because we're telling it to mimic this. Then the other one we looked at, and this is from the video you just saw, would be our, I'll say, hybrid zero dynamics inspired. I think inspired is probably the correct term because we're not doing true hybrid zero dynamics. But hybrid zero dynamics was a methodology that was more prevalent. I don't know, I want to say it's the 2010s, maybe something around that, with bipedal. They did this with a lot of planar bipeds. And the idea is you do the trajectory optimization, effectively the trajectory optimization I talked about earlier, and you generate a steady state periodic orbit. But the idea was that you had stable zero dynamics, and you would optimize for that in your optimization. Zero dynamics are really just the underactuated coordinates of the robot. So the idea is you make the underactuated coordinates stable, and then you would just have to track, and they would track these with nonlinear tools like feedback linearization or CLFs. You track that. You track the actuated coordinates. So we are doing, I'll say, the hybrid zero dynamics inspired trajectory optimization. We make a periodic orbit, and we make, in this case, a reference of libraries. We had, I think, 10 references going from 0 to 0.75. And then we just pull the reference that's closest to the commanded velocity. And that's what we track in the training. So then we can go on to the CLF-based reward. The idea here is we get our reference generator, which generates our YD and our YD dot. And these are parameterized by some alpha. Normally, this is like a spline. So you could think the output of the trajectory optimization is a set of splines that we're going to track. So they're continuous in time. And then we can construct our Lyapunov function V. So we denote eta here to be the output error. Outputs is a term that kind of comes from the HCD, methodology. It's effectively saying these are the things we're trying to track are the outputs. So eta denotes our output error, and then we construct a quadratic Lyapunov function. So that's v of eta. And like I said, this is actually, there's a proof in the paper about this, but this is actually a valid Lyapunov function for the system because the system's fully actuated. So it's actually feedback linearizable. So you can choose this. And then we want our v dot is less than or equal to negative lambda v. So we put these into the rewards, and I'd say like pretty standard RL formulation. So on the left here, this is just our minimizing the v reward, right? So this is, we just put v in this exp and we can, regularize it by some like sigma. And then on the right, what we end up using is this like clipped reward. And this is actually just a penalty. So one of the cool things about the CLF is that it doesn't specify a singular action to take. It specifies a set of U's, and any U that satisfies this decreasing condition should give you certifiable stability. And so we just wanted to encourage that we're within this set. So what we do is we penalize the training if it doesn't converge at least as fast as lambda v. And if it does converge, then there's no reward. It's just 0. So you get this like, kind of hinge term. And these are like our main tracking rewards. These are, I will say, different than just doing norm squared on every different term. Specifically, this Lyapunov one, putting it all into one term actually affects the numerics and the resulting tracking. And I have some plots on this in a later work where we studied this in more depth. And then you have the decreasing condition. To get this to work, we also have a regularization and a holonomic reward. So this holonomic reward is just saying the foot shouldn't slip when like the contact foot shouldn't slip. I have actually since been able to remove this reward. And to be honest, it doesn't really do anything having the reward, not having the reward, since it aligns with the trajectory optimization. So having it doesn't really do much. But for the original work, the paper we published, we did have it in there. And then the regularization, this is really just for deployment to hardware, right? So torque penalty, action rate, joint limit, kind of classic stuff, I think, for RL. And then what we've done is we were especially interested when we did this work on comparing it to the, I'll say, kind of heuristic, just like making up kind of reward term type RL, right? So this is like you just adding a reward terms to get the motion you want. And we were mostly interested in comparing this to those and not to like other tracking based methods, at least in the beginning. And so the nice thing about this is that relative to those methods, we've been able to reduce the number of rewards you have to even bother tuning by quite a bit. So we train
I have
it then.
a question.
Can
I ask a question? So could you go back to two previous slides? Previous slide. So about this CLF decay reward, I did understand what this term is doing. It's more like enforcing the V to be control reactant function.
Yeah. So this V dot is less than or equal to negative lambda V you see above it.
Yeah.
This term is just enforcing that inequality is always true.
Okay, because that's V should satisfy to be, control reactant function.
Yes, exactly.
Okay.
So to be converging to the origin, you need to be satisfying this condition. And so this reward it tries to enforce that condition.
Okay. Another question, what's the output Y in this case for your task for the
G1 so
locomotion?
We did a few different ones. The output was the pelvis position and orientation. So it's like the base frame. And then we did one where we just did all of the joints of the robot then. The other one you could do would be doing like the pelvis position and then all the end effector positions and orientations. And then it also included the velocities of all of these things as well. So the Lyapunov function encodes both position and velocity tracking. And then the decreasing condition has us decrease to this. So in some sense, the V dot term is on velocities and accelerations.
Okay. I guess if you include the position of the, so when you say position, it also includes the base position, right? Base position.
Yeah. So the base position, so it includes the base position, that's the pelvis, right? This is like our root frame of the robot.
Yeah.
And this is relative, all of the values were relative to the stance foot position. And
Okay.
this is because when we optimize like a long horizon periodic gait, right, we didn't want one trajectory that goes out for like forever, right? So when you stance, all of your frame positions are relative to your new stance foot.
I see. Okay. Thank you.
Yeah.
So quick question, Zach. I think this is very interesting. I think you said using this CLF reward help you to reduce the workload of tuning parameters. I guess is you are really referred to this omega v, this which is kind of just a scalar for the reward coefficient. But it's that looking at this Lyapunov function, v, you have this p matrix in the middle.
Yep.
Is that sort of you have to kind of design that p matrix, which is sort of like a kind of reward coefficient, I guess. But I think you use this exponential one, so I wonder, is that P designed that P is sort of equivalent to design the reward coefficients, in a standard way? And how you choose P, I guess.
Yeah. This is
Is
a
a
great
question.
question.
Yeah.
So P we normally get by solving the continuous time algebraic Riccati equation. So we effectively would set up like an LQR problem, and then you choose your Q and your R. So maybe you could argue we just made the problem worse. But I think it makes like a lot of sense to say, imagine I'm tuning a LQR problem for a double integrator, and I want to choose my Q and my R. That leads directly to P.
Mm-hmm.
And then what we do is we actually propose in the paper to compute sigma V. We use the eigenvalues of P and we estimate like a max error of eta. Like we max estimate a max value of eta. And this scales our Lyapunov function to be like roughly between, like 0 and 1. And we do the same with the clipping term, right? So we scale it so that our V dot plus lambda V, if we estimate a max error, is scaled roughly between 0 and 1. And then we use the eigenvalues of P to like do this scaling somewhat principally. I mean, I'm not going to claim it's like, groundbreaking or anything, but I think it helps reduce some of that decision. But you're right. The P
Mm-hmm.
does ultimately need to be created still.
Okay. Sounds good.
Yeah. I think also what we liked about this too, when you compare it to just, I'll say more heuristic RL methods, is just that it's like kind of principled in the terms, right? A tracking term, a holonomic term, stuff like this. And I think this is like kind of commonplace now. I feel like a lot of people just do kind of tracking RL, so maybe this argument doesn't hold up quite as well right now. But when we were doing this work, that's what we thought about kind of the most, I'll say. And then there was one other comment I'll just say with choosing the Y. You could also, so what I've done in more recent works is I've chosen my Y to be both the joint positions and velocities and the end effector positions and velocities. And this doesn't hold as well with, like, I'll say the classic CLF theory, where you would really just you have to be actuating on output. So your error needs to be on actuated outputs, because in this case, we'd be like kind of double dipping. But for RL, like practically, this I think helps. So the choice of Y is kind of up to you as designer. Okay, we train with domain randomization and Isaac Lab. We've got some basic like kind of terrain variations. We've got classic, friction and center of mass adjustments and all of that. And then we can compare this. So we compared this against the Unitree one here is the Unitree open source policy. Those rewards just put into our environment. It's not their like policy that they sell on their robots. That would be much better, I'm sure. And then the custom policy is the policy we cooked up in the lab before we did the CLF-RL stuff. And then we have the 2 CLF versions. And there's kind of a lot of things on this plot, so it's hard to see. But what we can see is that the custom policy and the Unitree policy have a lot more variance than this CLF-based policies. And so this was a good signal for us to say that I think we're getting some form of maybe like robustness improvement from this reward shaping. And just to be very clear, all of these policies were trained with identical domain randomization, observations, number of iterations. The environment was completely the same. So this also emphasizes that like the reward structure matters. I mean, it's hard to say a blanket statement, here's the best reward structure, but it does matter, right? And I think this shows it very kind of point blank. And then the question is, does the decaying term do anything over just the Lyapunov term? And we found it gave us some velocity tracking improvement. But being honest, I think the Lyapunov tracking term does most of the heavy lifting. But the decaying term is nice, as this comes from the CLF theory. So we deployed all of these policies then on hardware. So this is our lip CLF policy. It looks kind of like a lip controller walking around. The lip model doesn't tell us what to do with the arms. So we just fix them out there and then we can have it walk. This is our HZD CLF policy. So you can see it walks, maybe a little bit cleaner. It's using the full order dynamics optimization. And then here is our like kind of baseline policy that we had been using before. Just to show you that this does actually run on hardware, right? It's a real policy. So then we did some hardware experiments where we wanted to evaluate the robustness of these policies. So we loaded a backpack with different weights and we compared like the baseline method versus our HZD CLF method. And we used motion capture to get position and velocities. The motion capture was not used in the actual policy. It's just used for like analysis. And you can see here on the left, especially in that graph, that the HZD CLF is pretty spot on. I think there was some noise in the motion capture because the points were kind of hard to read. I think we didn't have the best setup when we did this, which is why it's like pretty noisy. And the baseline policy at the highest mass failed, and we couldn't even get it to run the complete course. It would just run into the wall. So like I said, well, the only difference between these two policies is the reward, right? And you get vastly different performance and robustness. And so I really think that just highlights that it's worth thinking about the reward structure. Okay, so we did then a little bit more with this. This is the same CLF-RL walking you're about to see, but we now did this multi-robot demo. This kind of was part of some work we did with some sponsors. And what we did is we attached this quadcopter onto the back of the G1. And then we had this thing walk around campus with this quadcopter. But this is not just a normal quadcopter. This thing can fly and drive. So combined on this, we have walking, flying, and driving. The idea here is that we'd walk it through the library because you wouldn't want to like fly the quadcopter and its driving is like slower than this. But then we want the quadcopter to be able to deploy off the back of the G1. So we can then bend over and we can have the quadcopter deploy. This bend over policy is actually a model-based policy. I'll come back to this a bit at the end of the talk. But the walking was all the CLF-RL stuff you just saw. Anyway, it can bend over. We have a backpack with some servos on it. The servos can release the latch, and the quadcopter can actually take off directly from the back of the humanoid, which is pretty fun. And then the humanoid can bend back up.
I think there's another group. I think Sandro's group. They have this flying biped. Do you think this propeller is strong enough to lift the G1?
I wish that would be very cool.
Yeah,
but no,
that's more challenging. I know.
I think some of the original concepts had the actual humanoid flying, but yeah, for now we've just settled on multi-robot.
Okay, this is cool. Very cool.
Yeah. So yeah, I think that was kind of a fun use case of some of this stuff, and we'll come back to the bending for a bit later. So I've used CLFs now, and a question I get from a lot of people is there any theoretical grounding? Like, do you get any kind of guarantees? I mean, you're using a CLF after all. So this is work that's not published yet. We're still working on it. It should be published very soon. But I'll share some preliminary results with you guys. So we started off by viewing the RL problem as a discrete time optimal control problem. And this is making a number of simplifications, right? I'm not going to claim that this is the exact problem we're solving. And then we are kind of looking at a simplified reward structure here. So this stage cost L is just linear in the Lyapunov function V. And then we have like the discrete time Lyapunov decay rate reward here. So this is doing the same. It's penalizing you if you're not decaying fast enough. And then we can formulate the discrete time infinite horizon discounted optimal control problem. And we've been able to prove theoretically with preliminary results here that we can get exponential stability to the origin if you use this cost function in this discrete time optimal control problem. And like I said, there's work to be done to really make this truly match the RL problem and whatnot. And we have this for the more, I'll say, realistic rewards, and even with the regularization rewards, we can recover this result with different constants, of course. And we've been able to numerically verify this when you solve the optimal control problem. So this is a good signal that this is like a pretty principled, or at least we think it's a pretty principled way to design these rewards. And I think there's so many decisions when you do RL that having some kind of grounding like this is important, as it can help alleviate some of these additional decisions you have to make. Okay, so we did walking. Can we push the speed? Was the next question we asked. And the answer is yes, we can push the speed. Still at this point, there's no human data at all. So we like this result because this is, I don't think I've seen a result that did really dynamic motions like this without human data in this kind of reference tracking RL paradigm. So I've slowed it down so you can also really see that we get the multiple phases of the hybrid system, right? We get the full flight phase, then we get the full single support phase. And then we can have this thing run on the treadmill, and I'll show you running outside too. How do we get the running? Well, it's a pretty similar pipeline. First, we do the multi-domain trajectory optimization. So the original trajectory optimization we did with the walking really just had one domain. It was single support back to single support. Now it's flight phase to single support back to flight phase. So we had to kind of improve our trajectory optimization pipeline to get this. Then we train in simulation with Isaac Lab, and then we can deploy it onto hardware. I will say that there's this extra R domain term that we had to add. And this term encompasses both the holonomic reward, which was the no slip constraint, and it also had a reward that penalized you if you were in contact when you shouldn't be in contact. So once again, these things were not enforced as constraints. They were just rewarded and penalizing you. And that was necessary to get us into the flight phase here. But it still was keeping with we're just using the nature of the hybrid system effectively. So we can deploy this outside. So this is it running, and we can get pretty good velocity tracking even while running. Maybe I'll pause this here. So first off, you can see we're still getting a full flight phase even outside, like real world terrain. And we're using a layered control stack to make this running go straight. So we use a LiDAR, and we get odometry data from the LiDAR. This goes to a high level PD controller, and then this goes to our CLF-RL running policy. And this keeps it going, at the correct, it keeps it running on a line, because it can be hard to joystick something with a flight phase by yourself. So this kind of leads to controllability of the policy, and this kind of like baby steps towards autonomy, I'll say. And then everything runs on board. So it runs, we took it outside a few times, and then we took it inside on the treadmill. And actually the treadmill, by the way, is surprisingly difficult to get it to run on because it's pretty thin, all things considered. So you don't have a lot of space for error. And we could do cool robustness testing. We throw wooden planks at it, and it can hit them and step on them. And it's pretty robust. Throw dodgeballs at it. The policy worked pretty well. I think this is traveling around maybe 2.2 meters per second, if I recall correctly. So it goes pretty fast. And you got to keep in mind, this is a small robot. The library of references we generated went from 1.1 to 3 meters per second, but we could only ever achieve at best maybe 2.7 or 2.5 on the hardware. It's difficult to really push the speed there with this policy. This really leads to the question, though, and what I've kind of been hinting at is, can we use human data? And can we get benefit from using human data? So in this next project, it's under review. It'll be posted on archive probably soon, but it's not out there quite yet. We put human data into the pipeline to see what kind of benefits we get. So we start with our reference library generation. This is We started off with kinematically retargeted human data that came from the LA fan dataset. We looked for a section in which the human was running, like running fast. And then we can programmatically identify a periodic subsegment. So we identify the most periodic single stride. This is checking the initial condition versus the reflected final condition. And then we can identify if it's in or out of contact by thresholding the foot above the ground, if it's a certain height or not. And then we do the same multiple shooting optimization we've done for the last two projects, but now the cost is just to minimize the error with a desired, minimize the error for this, like relative to the human data. But it's subject still to the hybrid dynamics constraint, and we can enforce state constraints. So this allows us to really clean up the data kind of for free and get periodicity and get reference libraries and all of that. I'll talk about this in a little bit more in a sec. We get our reference library, and then we can do, I'll say, kind of the same trick here, where we put our reference library. This goes into our Lyapunov function tracking rewards, where we have our minimizing our V and our decrescent condition. We train another asymmetric actor critic with PPO and Isaac Lab domain randomization, and then out comes just a policy pi. Once again, no CLFs, no references in the observation. It just takes the phasing variable and the desired velocity, and then of course, like it's, sent like joint state, things like this. And then we can deploy this onto hardware. Following up from my previous work, there was a big emphasis to be placed on getting this to work in an autonomy stack and getting it to work with a high-level controller. So we really wanted to investigate how we could get running, which has a full flight phase, to be controllable. And I'll show you some tables later on. And now maybe I'll show you guys here the running we get from the human data based, the optimized human data, I'll call it. And I think it looks a bit better than the non-human data one, right? I think when I made the original video, I thought it was really nice, and then we made this one, and it really kind of shows what the human data can do. So we could get more speed. In this case, we could get up to 3.3 meters per second on the hardware, which is pretty fast for this size of robot. And we could get more endurance. And I think it looks quite a bit better, right? So this is optimized human data being tracked with the CLF reward. This is in slow motion, so it's about, I think, a quarter speed or something like that. This is probably, I think this is speed going around 3-ish meters per second. Does the human data actually help quantitatively, though? And there's a lot going on in this plot. There's kind of like two ablation studies in one plot here. So let me break it down. First, on the right is just our optimized dynamic human data. That was effectively the previous project. And what we're plotting here is just the reference tracking error. So how well you track your reference. All of these policies are trained to track a single reference, not a library. So we can just evaluate their reference tracking, one particular one. Then we have just in the second from the right is the kinematically retargeted human data. This is no optimization. This is the periodic subsegment that we used for the optimization. And this is us tracking that. And then we have the kinematically optimized and the dynamically optimized. So we find is that the dynamically optimized in general provides us with the best reference tracking. And optimizing your data in general provided us with better reference tracking than just like naively using the human data. And then it was interesting because the dynamic optimization results are kind of all over the place. And let me break down then what the CLF and the mimic mean. So the CLF is our CLF-based reward. And mimic is what we were calling like this classic mimic style tracking. You just take your norm squared error. You put this into, I think in our case, we use 10 different norm squared error terms, and you tune each of those. So to tune the mimic results, I took the weights from the Boston Dynamics Zest paper, if you guys have seen that one. And then I took those and then I further tuned them for running. And this is the result I get. It's hard to say I tuned them, optimally or the best. So it's hard to truly compare across rewards, but we found that the CLF-based reward gave us better reference tracking. And we found that optimizing our data gave us better reference tracking. So this is a pretty strong signal to us that this like optimization and these reward structures all matter. So beyond just the reference tracking, what else does it buy you? Well, when we optimize the data, we can generate libraries from human data. So for all of the project here I'm showing you right now, I use 0.3 seconds of human data, right? Which is not that much. So another way you could view this as us being able to get more out of limited human data. We get to clean the data and we can enforce dynamic feasibility. I think a lot of people, when they grab human data, you have heuristics on stability and things like this. And the optimization and the dynamic feasibility really just kind of give that to you for free by convergence of the optimization. We get to enforce periodicity for locomotion tasks, which is going to be, I think, pretty much impossible to get just raw from human data. I mean, you might get close, but I think it's going to be impossible to actually get periodicity. And for steady state walking and running, that's what you have. We can then improve our tracking, and we can also preserve style over a large range of speeds. So the human data was going at about 3.6 meters per second, and we stretched this down to 1.1. And it worked for this whole like 2+ meters per second range. Okay, so this is a big table, and I'm sorry for this huge table of numbers here.
Zach, one quick
Yeah.
question. How possible you think you can have one RL policy for multiple different tasks or motions, like running,
Yeah.
walking? I guess sometimes it's maybe challenging to target, one policy for all tasks, but to a certain level, let's say running task, you can maybe vary the running speed but still using one RL policy. So how much, to what extent do you think the policy can be used for multiple tasks?
Yeah, another great question. I could not currently get a walking and running policy even in the same policy, which I was surprised about because I thought it'd be kind of free, I'll say, to do that. You got to keep in mind that in the observation, there's no reference. So I think that potentially there's like a representation learning kind of limit we're hitting here where the neural network has a hard time understanding it's almost like a discrete change when you go from running to walking. And I think it has a hard time getting this difference just based on the velocity change command. So I think it's possible, but I'll say this is future work and I'll talk about it a bit, but this is something I'm actually very interested in trying to solve.
Sounds good.
Okay, so we have velocity tracking. I mentioned we want to be able to control the robot and we want to make it so we can put this into an economy stack. So we did this, another big ablation. I'm sorry for all the numbers. I know it's kind of hard to look at here, but we checked with the mimic style rewards and the CLF-RL rewards. And then we checked just the just the kinematic retargeted human data. This is one reference because you can't make a library out of that with goal conditioning. And maybe I'm abusing the term goal conditioning here, but by goal conditioning, I just mean it's a velocity tracking reward. It's like a new reward that just tracks the velocity. And then we have our dynamically optimized library of human data. And then we have that with the mimic style reward here. And we found that this goal conditioning with the dynamically optimized reference using the CLF-RL gave us the best velocity tracking performance. And this is what you need, especially when you're running and you're going fast and you want to go around obstacles and things like this. And then since the kinematically retargeted human data is just a single reference motion, I also tried increasing the goal conditioning weight by 3x and it still wasn't able to outperform it. If you go too much higher, then you really lose your style and it starts to become not robust as a policy. And I found it can fall over. And so this is I've seen some papers do this in the past where they take their one human data trajectory and they try to scale it in the RL. So this is effectively a question of, can the RL do the scaling and the reference library generation that the optimization is doing? And I think the answer is no. So I think the optimization is a pretty critical step if you want to be able to track large references from single human data clips. So we took this thing outside. This gave us much more endurance than the previous result for running. And by endurance, I mean the motors didn't overheat as quickly because the Unitree G1 is not really designed for long range steady state running. The motors overheat. They overheat at about 130 Celsius and we run them right up into that. So we were able to go outside. The top one is about a 300 meter path. The bottom one is about a 200 meter path. It could go longer. You can see our velocity tracking. I think it's pretty good given, we're outside in real world environments. And I'll just show you some clips from these running here. What we're doing here is I'm driving it in, I'll say, the global frame. It's going at a set forward velocity, and then it tries to track a position with its local y coordinate. So like it adjusts horizontally to track a position, and then it's also tracking a global yaw angle. So it's like this in between like fully autonomous and me driving it. I'm giving it global set points, goes into a PD controller, which goes into the running controller. We're a bit bigger than the robot, so it's not quite as impressive, I think, when we're next to it running. But maybe you see the kids in the background running. They're closer size, and they're actually having to run to keep up with this thing. And for what it's worth, I don't know who the people in the background are. They just started running with us. So yeah, we can take this and we can have it run outside and like long distance runs. And this is another run just from around campus. I think it looks pretty nice. I think it's pretty controllable. And yeah, I'll let this play out here for a second.
Cool. This is very nice. And maybe while playing this video, I've been just curious. I'm trying to see where the ground reaction forces, it's part of this framework, or it's not. I haven't seen it anywhere in the
Yeah,
even the
so
reference, and so it's not explicitly considering ground reaction forces, I guess.
yeah, so the ground reaction forces are optimized when we do the trajectory optimization, but they're not passed to the RL. The RL gets effectively the kinematic reference
Mm-hmm.
that has dynamic information like encoded into it.
Mm-hmm, mm-hmm. So when we generate the references, I think you sort of mentioned this kind of contact implicit approach, but not really. But in that TL part, you have the contact forces as part of the decision variables.
Exactly. Yep.
Okay. Okay.
Yep.
I see.
Okay, so I was hinting at autonomy, and so we actually did it. This is now fully autonomous. There's no driving it at all. We used LiDAR to perceive the environment, and then we used model predictive control with control barrier function constraints as a mid-level planner. And this plans on effectively a single integrator model. And then this goes to our running policy, and it's trying to avoid this like cart and this mat here. And so this is it running. It's running at about 2-ish meters per second here. We since fixed some bugs in the MPC, and we've got it in sim going at full speed, like 3.6 around obstacles. And we expect that to transfer to hardware, but we haven't quite done it yet. So it runs around pretty nicely. I mean, you got to keep in mind, this is LiDAR perceiving the environment. There's a pretty big buffer on there, right, to be safe, and we didn't want it running into things. But yeah, this is fully autonomous obstacle avoidance while running in outdoor real world environments, which we were pretty happy with. And to show you, in case you think maybe it just like drifted or something, this is what it looks like when we don't use any autonomy. This is it just trying to go straight. It actually also kind of showcases some of the robustness here. We did a lot of running into boxes. We did a lot of running into things when we were testing this. So anyway, it was actually, navigating around obstacles. So if we kind of revisit some of the research questions I posed at the beginning, how can we achieve the best performance and how can we minimize tuning effort? So I would argue reward structure matters. We've found very good success with the CLF-based reward structure. I don't think it's a blanket statement that it's better than other reward structures. I think, like with most things in RL, it depends on the numerics. And so I think it works well in the situations we've seen, and we've been able to like tune it. But yeah, but I think regardless of exactly which reward is used, I do think it matters and it can affect your robustness and your performance significantly. And then we found that optimizing data, and specifically optimizing human data, makes a big difference. Can we achieve any theoretical grounding? So preliminary results suggest yes. We've got some things that kind of suggest you can get exponential stability in the discrete time optimal control case, with maybe some more work to get this to truly match the RL case. Do we need human data? So I'd argue no, we don't need it, but it's very helpful, right? It helps with performance and efficiency, as you saw before. But we could potentially get away with just trajectory optimization. And Can we reach autonomous humanoid dynamic locomotion? I think yes, we can, but you need to make sure your policy is controllable. So we found that velocity tracking rewards and optimized reference libraries were really key to get this to really work, even in the dynamic where you have a full flight phase kind of situation. So I'll maybe briefly talk about what I think are some kind of next steps and future directions, and then that'll be it. So I think maybe you guys saw this because I think Jun Hang talked to you guys, but this was not work I was directly involved in, but this is actually just on a branch of the CLF-RL code. So this is the lip-based reference generator that I talked about earlier, but now the lip is effectively conditioned on the environment. And then you can get this, and then this is tracked with the CLF based rewards, and you get this really nice, pretty cool dynamic stepping stone behavior. This is very early work. We're still working on doing the hardware transfer, but this is the similar idea where we take our linear inverted pendulum model, which we can generate references online. By online, I mean in the training, and we can condition that on the environment. And then we can do things like stair climbing and other stuff. And then since none of these policies ever take the reference as an observation, you don't need to do the lip-based conditioning online in deployment. You just do it during the training. So the sim results here are really promising. We're still working on the sim to real transfer though. Then this kind of comes back to this multi-skill and generalizability. So I've actually done non-periodic motions with the CLF-RL. So if you remember the bend over from the beginning, that was a model-based policy. Since then, we've redone it with the CLF-RL approach, and it's much faster. I don't know if you remember how fast the other one is, but if you look at the bend over here on the left, it bends over in like a second now, as opposed to before it was like 5 seconds or something. And then the drone can take off, and then we can lift back up, and that's the one on the bottom right. I have some slower, perhaps more controlled versions too. So this is non-periodic, right? We're just generating episodic motions. And since we use the trajectory optimization, this is very quick. I made the references for this in maybe an hour or two tops. And since we have state constraints, I can just add in a state constraint that says, get me to a specific angle, because we need a specific angle for the drone takeoff. And that's very easy. So the question then is, can we expand to many skills? Can we do dynamic transitions? And can we put this all into a single policy, which I think is some of the stuff I'll be working on next. And then lastly, can we improve the trajectory optimization so we don't need the human data? I personally don't love the idea of us, like the future of robotics being, let's always just have hundreds of people gathering data and effectively, if you ask me, doing the hard part of the robotics for the robot, right? And so the question to me is, can I do trajectory optimization that gets us the quality of human data without actually having the human data? So we've got some very, very early results here. This is some like single rigid body type trajectory optimization, and then trying to track this with full order, trajectory optimization. We haven't solved the problem yet, but I think this is a very promising direction for future work. And that's pretty much all. I'm happy to answer any questions. Here's some of the code links, although I'm thinking maybe the trajectory optimization code might be private. So if someone wants that, I can make it public or add you. I'll be at ICRA if anyone wants to talk there, and I'm happy to answer questions now or over email. Thanks, everyone.
All right, let's give applause. It's a very nice presentation. I just have a quick question. The last one about trajectory optimization, are you guys trying to incorporate some of this ellipsoidal centroidal momentum into the TO? I saw this ellipsoid there for this.
Yeah, so this is just a single rigid body in that case.
Okay.
And we're looking at, almost you could think of like a continuation type method potentially, going from like a simple model to a more complex model. But to be honest, this is all pretty early work. So we're still working on it.
Cool. Yeah. Yeah, we have some centroidal momentum work we published before for this very dynamic IGL jumping maneuvers, and then where we consider the modulation of this centroidal momentum matrix. So that might be relevant, to
yeah, I think that would be very relevant. We'll be sure to look at that.
Yeah. Cool. I guess we can open the floor for some questions if anyone has. I really like this talk. I think the presentation, some of the thoughts are very nice.
Yeah.
You say you're going to open source the treasure opt code for the G1. Is that it?
Yeah. I meant to actually make it public before I gave this presentation. There's actually no reason it
Oh,
should be
okay.
private.
Yeah,
I just need
yeah.
to make the repo public.
I'm really interested in this treasure opt code because like it's
Okay.
basically setting up the treasure opt for G1. Yeah, we are having some problems these days. Def Definitely a
Yeah, for
patch.
sure. I'll make sure that gets public. And for what it's worth, that repo is under development, but it's not too hard. It's a bunch of Python code, so I'm sure you'll be
Yeah,
able to figure it out. But yeah, for sure.
thank you.
Hi, Zach. Thanks for your talk. I think it's great. And they're very cool demos. I just have a quick question. So during the RL training, you take the CF condition as a reward term, right? So is there a way like to enforce it as as a constraint rather than like the reward term? Is it possible, or what's the trade-off between the
Yeah, I think it's very possible. We have some other people in our lab who have been looking at trying to make a control barrier function constraint part of the RL optimization. So like effectively projecting the PPO gradient so that it satisfies the barrier constraint. And I think you could probably end up doing the same thing with the CLF. But I will say that I don't actually think you always want the CLF condition to be satisfied. So when you do a classic CLF-QP, you get a region of attraction around your reference motion where you can, effectively come down this gradient and arrive at your reference trajectory. But this is actually like, this region is perhaps more limited than what you get if you let the RL choose something sometimes that doesn't satisfy the constraint. And so I think that's why it's nice to put it in a cost, is that you are encouraging the behavior, but you're not enforcing it. So if it needs to make a different decision that leads to more stability, it can do that. So in practice, right, we get much bigger regions of attraction with the RL than we do with like what people had seen before with the CLF-QP approaches.
you mean just like add it as a like a reward term may give like a more flexibility, right, during the training.
Exactly. Yeah.
Okay, got it. And another higher level question is how scalable it is like to like scale your pipeline to some like local manipulation like motions, right? More diverse like upper body, some manipulation task, right? Especially for some like contact with the other parts of the body rather than the foot position. It's like yeah, just
Yeah, so on the RL side, I think it could handle all of that. We haven't done a lot of loco manipulation. I'm kind of interested in it, but I haven't done much of it. I think the problem would be on the trajop side. You have to make sure you're modeling those contacts, and if you're modeling this as like a hybrid system on like with multiple shooting, your hybrid system graph becomes much worse, and it becomes much harder to know a priori what the correct sequence is, which is how you can avoid the mixed integer program. So I think you'd encounter more issues on the trajectory optimization side. The RL side should be pretty plug and play. But I think if you are willing to pull just straight up human data, or if you're willing to, if you can work around this on the trajop side, I think it would work fine.
I see. So currently, the treasure part is in the loop of training, right? During like
The trajop itself is not in the loop. The trajop, we generate the references offline before training. The only
okay,
time the references are generated in the loop is when we use the reduced order model.
I see. So the data is offline, and
Yep.
then I got it. See, yeah, thanks.
Mm-hmm.
So the leap model one, you can just run this TL, in a kind of MPC fashion, right? Online. So just is that
Yep.
okay? Okay. So I still have this question. I'm trying to see why this CLF based RL is performing better than the baseline. And you talk a little bit about this safety grounding and formal guarantee. I'm still trying to understand a little bit more, how this CLF part works. Like it's literally you have this reference trajectory, and then given this CLF, it's going to, as time goes, you have this exponential, stability, right? So it's finally going to converge to the equilibrium or this reference trajectory you have. So does that mean that for the reference trajectory length in terms of time, the longer, the more stable behavior you are going to reach because you give more time to converge because you have this exponential convergence, right? And how much it matters for the trajectory length will actually influence your actual safety perform. I don't know, like
Yeah.
I'm not sure I asked the question correctly, but I think because you have this exponential convergence, and then to me it seems the longer the trajectory it is, before you switch to the next maybe periodic motion or something like that, the longer the better, in terms of the formal guarantee.
Yeah.
Is that true or like I'm or it
So
doesn't
I
really
haven't
matter much?
studied this exact question, but I can tell you what I think about it. I think it's probably the length of the trajectory will not make the CLF-RL stuff better than other reference tracking motions. I think they would perform similarly because I think in practice you probably get stability of the other methods. Two, you maybe just can't prove it, right? By using this
Mhm.
like Lyapunov theory, we have tools that we can actually analyze. And that's one of the things we like about in the lab is that we can actually analyze this method. My guess is the other ones you get similar stability. What I think happens and why the reference tracking looks better is because that the Lyapunov reward, when it's a single reward, you have to bring down the error of all of your terms together, right? Because if I have a joint that has really bad angular velocity tracking, that's going to blow up my Lyapunov reward. Whereas when I break this out into 10 separate norm squared error rewards, I can track my pelvis position, say, really well, and I could track my angular velocity on my knee joint really poorly because they're in separate terms, right? And so I really think that what happens here is that this Lyapunov approach enforces bringing all of them down together.
Mhm.
And so if you actually look at the individual sub-tracking plots, sometimes on some things you track a little worse with the Lyapunov reward, but with other ones you track much better. And so in no total, the norm squared error comes down.
Then I think it go back to the P matrix design, right? That's
Yeah.
that okay. Okay,
Yeah, and
that's
so
great.
just for what it's worth, the P, I pretty much use Q and R as almost all identity. I think
Hmm.
I bring some of the joint velocity or like I do a little bit of scaling just to make sure things are like roughly scaled to the same order of magnitude. But Q and R are just identity with like some of the terms being maybe 0.1 rather than one.
Hmm.
And that works pretty well.
Cool.
I have another question. So I think it's kind of follow-up question of what the EA asked, but for the first part of the talk, right? You added some payload to the G1, and then you compare the baseline controller and your CLF
Yeah.
tracking RL. And seems like or your methods is more robust to the payload. So what do you think is the reason? Because I guess during the training you apply the same domain randomization to the base policy and your policy plus. During the deployment, your policy seems to be more robust to the added mask, right? So what would be the
Yeah.
reason? Would be the explanation?
That's a great question. And I think it's really hard to answer. So with the baseline policy, we had classic terms, like there was a phase reward, there was like a height reward for the base, there was like a velocity tracking reward, a few regularization rewards.
Mhm.
I can't say exactly why. I mean, except for, right, the only difference was in the reward. You're right. We use the same domain randomization. So I think that the reward is just encoding a more stable behavior. And this like kind of makes sense because especially if you think about this tracking of a reference trajectory, you're really, you're telling it to always come back to this trajectory. And maybe with the kind of heuristic reward design, you don't quite get that same level of, I'll say, convergence. But I think it's hard to say for sure.
So your policy has whole body joint tracking, right? Is that right? So in your output of the CLF, you have joint trajectory velocity. plus
Yeah.
some n vector. Right?
Yep.
Okay. That might be helping the RL to
Yeah.
understand to be more robust.
Probably.
Okay. Thanks.
Okay, sounds good. I think we are close to the time. If we don't have any other questions, I will say thanks, Zach, again for this nice talk. We'll share the recording with you, and hopefully, see you at ICRA, if not earlier.
Yeah. Thank you for inviting me. It was great being able to talk to you all.
Yeah, we should definitely catch up more. Okay.
Yeah.
All right.
Sure.
Thanks, guys.
All right.
Yeah.
Bye.
Bye-bye.